Hi everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 3 of Bode plots. Previously we learned like how to do the approximate or asymptotic Bode plot. Here we'll understand more about Bode gain and phase plots, understand a bit more, and also plot few different functions like plot few Bode plots for different functions. We'll do with example, and we will understand how to plot the Bode gain plot and how to plot the Bode phase plot with a particular step procedure. Okay, previously what we were doing was we were just understanding the concept between the behind the Bode plots. Here we will understand the steps, because like obviously we don't have to think that much when we will plot the Bode plot. We will have to just think few things, and we'll just simply we'll just have to follow few steps, and we can simply plot the Bode plots. But before that, we had one question left, this one. We had to plot the Bode plot for this function g of s equals to 1 plus s tau. So I hope you have done your homework, like or you have already got the notes, so like that is already present in the notes. So this g of s, so what is this g of s? If I put j omega, simply it will be the inverse simply, because like everything gets interchanged. If like I have 1 by 1 plus s tau, now I have 1 plus s tau, so it becomes inverse. So if I replace g of j omega, one plus j omega plus tau, then what will the magnitude function be? So magnitude function will be one plus omega tau. Okay, magnitude function will be 1 plus omega tau whole square. Okay, this is my magnitude function basically. So like what will be the log value? Log value will be again in dv's 20 log under root 1 plus omega tau whole square. Now what we can do is again do the high frequency and low frequency analysis. So like for these two questions only I'm doing this. After this obviously we won't do this every time, right? We understand that yes, high frequency something will get approximated, low frequency something will get approximated. So low frequency region, what is the low frequency region? My omega is much less than 1 by tau. Then if my omega is much less than 1 by tau, that means that my omega tau is much less than 1. Okay, so my omega tau is much less than 1. That means that we can approximate this like this. So my magnitude becomes 20 log 20 log 1 itself, so it is almost equals to 0, because log 1 is 0, log 1 base 10 is 0. So yeah, this is low frequency region almost goes to 0. What about my high frequency region? Much greater than, omega is much greater than 1 by tau. Hence omega tau is much greater than 1. Now if my omega tau is much greater than 1, what does this mean? This means that my magnitude of j omega will be like this, will get ignored, 1 will get ignored, so it will be omega tau whole square. Under root that is omega tau, so 20 log omega tau itself, 20 log omega tau. Now this is like, this will be like a slope of straight line with 0, simple, like as we got for s, simple s over there, sorry. Okay, simple s. So this is 20 log 10 omega tau. And what about my phase angle? What happens to my phase? So omega is much less than 1, so obviously my phase, let me write the phase expression. So phase becomes simple this time, plus tan inverse omega tau. Okay, so my phase becomes plus tan inverse omega tau. So here this becomes angle, this is omega tau is much less than 1, so almost angle will be equals to 0. Tan inverse 0.1, tan inverse 0.001, it almost tends to 0. Now what is happening here? It almost tends to 90 because it is much greater. It almost tends to 90. So yeah, this is it for this a value, basically for this value. Okay, so now these are the things. Now let's actually plot the gain plot and the phase plot. Both will compare with both the exact and the approximate analysis. So like exact, I will just give you a brief idea how the exact one looks. Obviously I don't even also know exact what looks like exactly this passes from this point. Obviously we won't be we won't care too much about that, but just to get a brief idea. So this is omega, this is magnitude of g or j omega in dBs. Okay, and like the exact plot will be something like this, just the inverse of this one. So we start from here, okay, and okay, initially it is very low, then it suddenly increases like a parabola itself. Just remember this is a log scale, right? This is in log scale, that's why it increases like this. Okay, it gets like this. This slope won't be that high, this will be something like this. Okay, now what is this? So what my Bode plot? So Bode plot will be until this corner frequency, it will simply have what, 0 dB. So this is let's say this is 0 dBs. So until the corner frequency it will have 0 dBs. That is what we approximated here, right? Before this corner frequency we'll approximate it as 0 dB. So it is 0 dBs. Next the slope changes, slope becomes 20 dB, plus 20 dB per decade. Okay, here the slope changes to plus 20 dB per decade. So slope changes to plus 20 dB per decade. Okay, so they almost intersect with each other. Okay, like this. So here my slope is plus 1 dB per decade, and like this is my error. And if you calculate the error again at this corner frequency, you will see that it is a 3 dB error. So like this is my exact plot, and this is my approximate plot. And this is my 3 dB error. Okay, so yeah, this is about this case. Obviously the approximate plots intersect here. Okay, we have plotted the low frequency and high frequency region. Now let's plot for the frequency response. So one thing I forgot to mention, like this slope, right? We linearly approximate this slope. Where did it go? Yeah, we linearly approximate this slope, and this the slope of this one, that we chose was 45 degree per decade. Why? To make the error at this corner frequency 0. If we choose this one as 45 degree, like here my like the magnitude is 45 degree per decade, here like the direction is opposite, so minus 45 degree per decade. So if we choose this one minus 45 degree per decade, what happens is 1 decade I travel from 0 degree, I travel to minus 45. So exactly the error becomes 0. That's why we choose our slope like this, minus 45 degree per decade. So here the slope of this line degree per decade. Like this is just my hypothesis is just to make the error zero at the corner frequency. Okay, just my hypothesis. Nothing. This is nothing like it's written in book. That's what I think that Bode thought when he invented this slope. Right. That is what I thought. I think that he thought. So yeah, this is my hypothesis to make the error at corner frequency 0. Okay, so this is the slope. So here also the slope will be here slope was minus 45 degree per ticket. Here the slope will be just inverse of that one, so plus 45 degree per ticket, and the phase part I am talking about. So just let me draw the axes. So if I draw the axes, this is angle of g omega, and this is omega, and like let's say this is 0 degrees, this is 45, and this is 90 degrees. Okay, so this 0, 45, 90. So my exact plot will look something like this. So what is exactly this? Tan inverse omega tau. So it will look something like this. Okay, it will look something like this. Like I won't be say I won't be able to plot exactly like that, but just understand the shape will be something like this. And what are the individual points? So let's say this is some individual points. This is 0.1 divided by t. Okay, or here I would have written tau, right? So this will be tau itself. 0.1 divided by tau. This is 1 by tau, and this is 10 by tau. Okay, so now what does this become? So basically what happens, this shifts by 90 degrees, that we understand, right? So it shifts by 90 degrees, and like this is the exact plot, and this is the here, right? This is the approximate plot. Yeah, I've written. One more thing is that like the slope, right? The slope is minus 45 degree per decade between these 2 points, like between these and these 2 points. But after this, the slope becomes 0. That is also an important step to understand. The slope doesn't, like, slope changes also. Okay, that also we have to take into account. So here here also slope is 0 degree per decade. So yeah, these are the slopes basically. So what is happening in up here? So what we're assuming, like if we would have gone with the old approximation, what we would have told is it is 0 until here, then suddenly it becomes 90. Okay, suddenly changes. But we have found out a better approximation. So here what is happening is that it is 0 until here. Okay, now what is happening is it is going straight line like this. Okay, obviously I won't be able to draw it perfectly. If I will get a prize, but obviously I will not be able to. I have to make a few like changes here. So what I will do is just make a few changes. I have forgotten how it looked like. So I think it will look something like this. So like obviously I wasn't able to draw it exactly like this. So just hold on a second. This is so bad. This is so bad. Sorry. Just wait a second. Uh, yeah, it goes like this. This also again the slope becomes 0 for this, right? They both of them intersect. So okay, this is the exact plot in the bottom. Okay, and this is not dBs. This is 0 degrees per decade, and this is also 0 degrees per decade. And this is plus 45. From minus 45 this become plus 45 degrees per decade. Okay, so yeah, this is the approximate plot. Okay, here we see that this is the corner frequency. So these are the plots, I think. So overall you can see that this has shifted up by 90 degrees. All these things I hope you got, right? You got the main crux of this. So now let's go for the start of the lecture 3. So before starting the lecture 3, what is the main point I want to tell is that what type of questions will come in this chapter. So until now what we have done, we have plotted the Bode plots for few transfer functions, but largely what type of questions come. So two types of question mainly from Bode plot can come. Also error finding error, few miscellaneous topics are there obviously from Bode plot, but major portion is these two topics, where like the major portion covers is this one. What is the this first one? This is the first one and the second one. So here first one, what they're talking about is that you have been given the Bode plot, you have been given the Bode plot is given to you. You have to find the transfer function. So this is also known as the recovery of transfer function from Bode plot. This topic is also known as recovery transfer function from Bode plot. This we will understand after obviously this one. Okay, like this is a hot topic. So Bode plot will be given to you, only the magnitude plot or the phase plot or like both. It depends. Now it's given to you. Now you have to find, like you have to recover the transfer function from that. How will you understand that? That obviously solving few questions we will understand. Like first we have to understand how to plot Bode plot. We have plotted few Bode plots for few of the transfer functions, but rest if we plot more, then also our concepts will get more cleared. So what is the second type? Second type is transfer function is given and you have to find the Bode plot. So that is what we have been doing until now. Okay, for a few basic examples. Obviously we'll do for difficult examples also. From there our concepts will get more crisper and clearer. So like what are the weightage of these two? Okay, what are the weightage? Obviously there are a few miscellaneous topics. I'm not talking about them. Those will come later. So the weightage of these two, this one almost comes 90% of the time. This one comes, and this one comes for 10% of the time. This one comes for the 10% of the time. So this one almost comes for 90% of the time, and this one almost comes for 10% of the time. So it depends, right? Which one? This one has higher weightage. This one has higher weightage. So Bode plot will be given to you, and you have to recover the transfer function from that. What was the transfer function for which the Bode plot was given? Okay. So yeah, that all those things will solve. But I just wanted to give you a brief overview of what are the most important topics. Okay. So now let's I have summarized few key points about the Bode plot, whatever we have understood till now, whatever we have done till now. So what we have understood about the Bode gain plot: a pole gives me slope of minus 20 per decade. That we have understood, right? Whenever there is a pole, even if it's at s equals to 0 or it was at s equals to 1 by tau, this newer example, but I got a slope of minus 20 dB per decade after the corner frequency. So a pole gives me a slope of minus 20 dB per decade. A zero gives me a slope of plus 20 dB per decade. Same reasons. Error will be maximum at the corner frequency with respect to the exact plot. Okay, 3 dB that we have already found out, calculated with intuition also. The slope of the magnitude plot would tend to minus 20 minus n dB per decade as omega tends to infinity. So if you don't understand this, don't worry. We will solve questions and from there you will understand this. Okay, like this is the error here is 3 dB. 3 dB error. Okay, maximum error is 3 dB. Okay, like if you don't understand this one, don't worry, don't have to understand. This is just for the written context. Obviously when we will solve question, there you will understand. Okay, what does this n minus n mean, represents here? So here I should write this, that n is the number of poles, m is the number of zeros. So let's say if I have two poles and 1 0. Okay, so the two poles are contributing each minus 20 dB per decade and minus 20 dB per decade slope. Okay, as omega tends to infinity, like after corner frequency obviously, but as omega tends to infinity, all of them has cross corner frequencies. All of the poles has cross corner frequencies. So poles will contribute total how much slope? Minus 40 dB per decade. Now I have also another 0. Now 0 will contribute how much slope? Plus 20 dB per decade. So total how much slope I am getting at omega tends to infinity? Minus 40 dB per decade plus 20 dB per decade. So it becomes minus 20 dB per decade. Hence the formula is like this one. Like what does this mean? So 2 minus 1 into minus 20 per decade, total I am getting. Now if my 0 is more, obviously I will get positive slope as omega tends to infinity. If my poles is more, I will get negative slope. Now if my 0 is more, what does this mean? I am getting positive slope. I am getting positive slope. So my magnitude is keeping on increasing. Is that even real as well for real systems? For real system at infinite frequency, I am getting infinite magnitude. Is that even real as well? That isn't real as well. That's why I told you like throughout this control system theory that my number of poles should always be more than number of zeros for practical realizable system. Okay, real life systems that we use. So always like number of poles will be greater than number of zeros. N will be always greater than m. Okay, obviously theoretically we can do anything. Here in question control system they may give some transfer function which has more zeros than 4. That may happen. No worries. But practically that is the main thing. Okay, that is the main thing. Now here also I have written the few key points about the Bode phase plot. This is very important. Do listen to this very carefully. People don't tease this. Okay, they just skip this part and some question comes up in gate and everyone is confused, everyone is running. Okay, so just listen to this very carefully. I already explained this like while drawing the Bode phase plot. Here also let's understand the key points very carefully. A pole gives me a slope of minus 45 degree per decade, but between what? Between what is the range of this slope? This is not always. And like here slope like a pole gives a slope of minus 20 dB per decade as my omega is greater than my corner frequency. Okay, when my omega is greater than my corner frequency, or here when my omega is greater than the corner frequency. So I'm assuming this as corner frequency, or like the frequency at which the pole is present. Okay, like 0 pole, whatever is here. This is omega z and omega z. I hope you understand. This is pole and this is 0. Okay, here what is the key point? Here my what is the range between which the slope is present? The range is 0.1 omega p. P is the pole frequency. My omega should be greater than this and my omega should be less than this 10 omega p. Okay, this is the range for which this minus 45 degree per decade slope is present. Very important. Now angle contributed to pole for omega less than 0.1, this is 0 degree constant. So here my slope becomes 0. Slope 0. Okay, that's why this range is given here. Omega less than 0.1 omega p, slope becomes 0. Omega greater than 10 omega p, slope becomes minus 90. Again right here my slope is 0. Okay, now a 0 gives a slope of plus 45 degree per decade. A 0 gives a slope of plus 45 degree per decade. So this is the same thing, only range will be same only. The range will be omega z and angle contributed to 0 again, right? If it is less than omega 10.1 omega z, it is 0, and like slope is 0 obviously. Slope is 0 obviously, and here my slope is again 0. Like angle contributed as omega is greater than 10 omega z, it is 90, and here the slope is 0, and here the slope is 0 again as it omega is less than 0.1 omega z. So yeah, this is very important, very important. Do understand this. So someday, like obviously questions have come in Bode phase plot and people have messed up, so you have to read all this point very importantly. So my slope will be present between 0.1 omega p, like between the 0.1 into corner frequency and the 10 times the corner frequency. 0.1 times the corner frequency and 10 times the corner frequency. The slope will be present minus 45 degree per ticket or plus 45 degree per ticket depending on the zeros or poles. Very important. Okay, this is about a single pole. Now what about if I have multiple pole present over there? If I have multiple pole present over there, it will be simply multiple of that. So like if I have two poles, it will be minus 40 dB per ticket. That also we'll do. That also we'll do in examples. There you will understand. So yeah, this is about this one for a single pole. Okay, also another key point we have, error will be minimum at corner frequency, which is 0 degree, and the phase of the g of j omega would tend to minus 90 into n minus m theta as omega tends to infinity. Now where n is my number of zeros and number of poles. N is my number of zeros and number of poles. So minus 90 into n minus m, what does this mean? So this means basically like you understand, right? So basically I have, let's say, 1 0 and 2 poles. So at omega goes to infinity, what will happen? That those tan inverse terms in the denominator, okay, minus tan inverse terms will give total minus 180 degrees, and the one in the numerator tan inverse, that will give me plus 90. Minus 180 plus 90 is minus 90. So here minus 90 times 2 minus 1 is minus 90. So from here you can understand we have done polar plots so many times, so this is just a cakewalk for you guys. So I don't think I have to explain it very further. But what is the important point to note here is that it is only valid, this formula is only valid for non-minimum phase system. So we'll understand now what do we mean by non-minimum phase system. Yeah, sorry, actually I was recording until now, okay, like for 10 minutes, and like I just went out for in the washroom, and what happened, I moved the mic and I forgot to put the mic again back near my mouth. So I was recording for like 10 minutes, and like it wasn't like the voice wasn't picking up. So I will, like, we are here until here, right? We derive for non-minimum phase system. Then like we had a question, okay, like I had a question. So we have to plot the Bode plots for the following function. So we have to plot the Bode plot for this following function. So obviously I will tell you the step-by-step guide of what we need to do. Okay, obviously I will tell you that, but first let's solve it on the go, and then obviously I will write all the steps how to solve it and what things to keep in mind, right? So first what we'll do is obviously find the DC gain of this one. So if we find the DC gain of this one, then what happens? Then simply you can get to the first stage, that what is the DC gain, like, and then what you do is convert it into standard time constant format. What is standard time constant format? We have already learned this in the chapter 1. I've told you. Obviously I will this is also written in the notes here in the next few slides. Standard time constant format is like that. It is DC gain times s tau 1 plus 1 divided by s tau 2 plus 1 into s tau 3 plus 1. That is written. Okay, I hope you understand that. Now after converting that, we'll divide it into fundamental blocks and we'll solve each of them separately and then add them up. Okay, now this is just the first example, that is why I am doing it so slowly. In the next few things we will do it just in 1-2 minutes. Okay, here I am doing slowly to understand everything what is actually happening in the Bode plot and why does the Bode plot characteristics is like that. Okay, so first what we do is convert into standard time constant format, or you can find a DCN also. How to convert this? Simply, like I was writing all this, but after 10 minutes I got to know that this mic was away from me. So what we do, we just take common all these terms, right? So how to convert this standard time constant format? This term in addition with the s tau should be always 1. So here it should be 1, so we have to take common 100. Here it should be 1, we have to take common 0.1. So we take common 0.1 here, we take common 100 here, so it becomes s by 0.1, s by 100. Okay, and this 0.1 can go above. Okay, this is actually 10, or no, this 0.1 times 100 is what, 10. Hence, like in the numerator it becomes 0.1 itself. 1 by 10 is 0.1. That is one case. So DC gain is 0.1. Now what does like we can write this like s by 0.1 like this, 10s plus 1, this 0.001s plus 1. These are what, s tau 1 plus 1, s tau 2 plus 1. Now we converted this into time constant format, standard time constant format. Now what we can understand from here is that like these are my corner frequencies. Like you can stop here also, you can stop here also, it depends on you. We will solve more questions and we'll understand like get an idea which one is preferable for you. So now we found the corner frequencies, we found the DC gain. Okay, now what we do, we divide this into 4 blocks. Okay, these 4 blocks I know how to plot the Bode plots for each of them. I've already plotted them with examples. Here this is 0.1, this is a constant magnitude, the first example that we did. This is like the previous example that we did, 1 plus s tau. Okay, this is 0. So what does a 0 give? 0 gives a slope of plus 20 dB per decade just after the corner frequency. I hope you understand that. Now this is a pole, 1 by 1 plus s tau. So this will give me a slope of minus 20 dB per decade just after the corner frequency. What is the corner frequency? Corner frequency is this 0.1, not this. This is the time constant, not the corner frequency. Corner frequency is the inverse of this one. So 1 by 10 is 0.1. 0.1, right? Now what is this? This is 1 by 0.001s plus 1. Okay, so this is another pole, so this will also provide me another a minus 20 dB per decade slope. So these are 4 components and they will be simply added. So I was just breaking them down. So first one was 0.1, so which has a constant magnitude, and like constant, we have done this in the first example. For constant magnitude, the Bode plot remains constant and we just have to convert it into dBs. So in dBs, like 20 log 0.1 becomes minus 20. And what about the phase? As this is positive, k is positive here, hence the phase is 0 degrees, no phase change. Phase plot is constant for this one. Now what about the 0? For 0 the corner frequency is 1 radian per second, as we can see from here, simply s by 1 radian per second. And what is the magnitude? The magnitude has the slope component, right? So slope is plus 20 per decade for a 0, and it is applicable after the corner frequency itself, 1 radian per second. Okay, now what about the phase? So phase is very important. Phase is very important. Now it provides me plus 45 degree per decade of phase slope. Okay, slope is plus 45 degree per decade 10 times before my corner frequency and 10 times after my corner frequency. After that it is 0 degrees. Phase becomes, it gives me 0 degrees. So after that slope becomes 0 degree per decade for omega greater than 10 and omega. It is understood that these are all in radian per second. I'm not writing this again and again. 0.1. Okay, so the slope becomes this. So these are about the phase and slope of the 0. Now I was just solving the poles basically. Okay, here I have pole. Corner frequency is what? Corner frequency here is 1 by tau, which is 0.1 radian per second. 0.1. And what happens with the magnitude? So the magnitude becomes minus, like the slope becomes minus 20 per decade after 0.1. Okay, and what about my this phase plot? So phase plot, the slope becomes minus 45 degree per decade between what? Between 10 times before the corner frequency and 10 times after the corner frequency. So it is simply 0.01 to 1. Okay, so this will be my slope, and after this my slope will become 0 degree per decade. Okay, after and before this, so in the range of omega less than 0.001 it is 0, and omega greater than 1 it is 0. Slope is 0. Okay, it remains constant over there. Same thing for the third block basically. So simply all of this will get added. So here, like what is my pole? My pole is this 1 by 0.00s plus 1. So zero point 0.01s plus 1. So this is a pole. So this becomes 100. This becomes 100. 100. So like here obviously the slope is minus 20 per decade, but it is after the 100 per second. So omega here after 100 per second, the slope is minus 20 per decade for this particular. It is contributing minus 20 per decade for this particular pole. Now what about this phase? So phase also is contributing minus 45 dB per decade, but what is the range? Range is 10 times after this and 10 times before this. So 10 times before this and 10 times after this will be, it has to be more than 10 and less than 1000, and below 10 and more than 1000 it is 0. It is giving me 0 slope. Okay, so these are the things that we have to keep in mind. So these are the fundamental blocks basically. Now like we can write it in table of slopes, so you don't have to do all this, right? But sometimes for Bode phase plot I will recommend you doing this, but Bode gain plot you don't have to do this. Just because we're doing this for the first time, we'll add all this. So at like what are the corner frequencies? So we will go from minimum to maximum. So here this one doesn't have any corner frequency, obviously constant magnitude. This one has a corner frequency of 1 radian per second, and this one has a corner frequency of 0.1 radian per second, and this one has corner frequency of 100. Okay, 100. So we'll go from minimum to maximum. So 0.1, 1 and 100. 0.1, 1 and 100. So 0.1 radian per second. Now if you have a 0.1 radian per second, what does that mean? Now this so at 0.1 radian per second, after that what slope we are getting? We are getting minus 45 degree per decade just after 0.1 radian per second, and we haven't reached our 1 radian per second yet. So the slope, overall slope, not minus 20. Okay, just it is in dB per decade, and like I will say this slope, I should write this overall slope of Bode plot. Okay, now like this is 0.1. Now let's do for omega equals to 1 radian per second. So for omega equals to 1 radian per second, my slope is already minus 20, and I have to add few things. At omega equals to 1, I'm getting a 0. Which is also contributing plus 20 per decade. Now that pole was already contributing minus 20 per decade, and the 0 came at 1 radian per second, and it is contributing plus 20 per decade slope. So obviously what we do the algebraic sum of these two. So minus 20 plus 20 becomes 0. So here it becomes 0. Here I had only pole, here I have pole plus 0, and here what is omega equals to 100 radian per second? What is like after this, yeah, the slope is 0 only until we reach omega equals to 100, we encounter another pole. If we encounter another pole, what happens here? Again, this pole is contributing another slope of minus 20 dB per decade. We had a pole which is contributing minus 20 dB per decade. After that, we had a 0 which is contributing plus 20 dB per decade. And after that, we have a pole here which is contributing minus 20 dB per decade slope. So overall, how much is my slope of the Bode plot, Bode gain plot? It is minus 20 plus 20 minus 20. So minus 20 dB per decade. Overall, this is the slope. Okay, so this is pole plus 0 plus pole. Okay, so here I have drawn the characteristics. You can just pause the video and check for yourself that what is this line. This line is a constant magnitude line, and this line, like, these are the individual Bode plots for the individual blocks. Okay, so individual Bode gain plot this is. So scale is, remember, scale is decade scale, don't forget the scale. So nothing is written, but scale is decade scale, but these are written in radian per second. Okay, and this is the constant value. This is what, this is the 0. This is the corner frequency. Corner frequency is 1 over here, so I should change this a bit here. Yeah, here. So the corner frequency is here. Okay, like it is getting a plus 20 bit slope, decade slope at this corner frequency, the 0. Now this is the pole. Okay, this is giving a minus 20 bit decade slope at 0.1. Okay, and this is another pole. Okay, this is another pole. Like all of them are starting from 0 itself. Only this one is starting from 0.1 because this one is giving me constant minus 20 per decade. All of them are starting from 0. Okay, and this one has a corner frequency at 0.1. This one has a corner frequency at 100. So I should move this 100 a bit, or yeah, I can move this 100 a bit here. Okay, like if this is not exact, I wasn't able to draw this exact, but just I hope you get the idea, like what I am trying to say here. So here, this is another pole, this is another pole, and this is a 0. Okay, and like these are 3 plots and 4. So we have 4 blocks here, 4 colors, and I hope you get the point that this is contributing, like the corner frequency here is 100, corner frequency here is 0.1, and the corner frequency here is 1. This is contributing a slope of plus 20 dB per decade. This is contributing a slope of minus 20 dB per decade, and this is contributing a slope of minus 20 dB per decade, but after the corner frequency, and this is constant. Now let's actually draw the Bode plot for each section. So between 0 to 0.1, we don't have any change, everything is constant, just that our plot is getting shifted down to minus 20 dB. So if I plot the Bode plot, so it will be something like this until 0.1. Until 0.1. Here also I am saying until before 0.1 I don't have anything. After 0.1 my slope is changing. Okay. So after this, what is happening? This is constant, this doesn't change, but here my slope reduces. Up until 1 my slope reduces, and these 2 slopes are constant. So obviously we are adding all this, so obviously I will take care of this slope. If you just simply add all this, the function will be like this, that the slope becomes minus 20 per decade as others have slope 0. So if I add all this until 0.1, it will come to minus 20 dB per decade. Okay, until 0.1 it will come to minus 20 dB per decade. Now what is happening after this? Let me just check one thing, that what is the value of the magnitude at s equals to 100. If I can, this is 102, this is almost 1000, this is also 110.1, very low. Okay, it will go to negative. Okay, so it will cross the sign. So here at 1, what I am getting? At 1, what I am getting? So at 1, this is the case. Now what is like after this, what is happening? At 1, the slope here, currently the slope is minus 20 per decade, but just I encountered a 0 also, and the slope becomes plus 20. So here the slope is plus 20, here the slope is minus 20. So overall the slope will be 0 simply. So one thing is going here, other thing is going there, then overall I go through middle. So physics motions here we have studied, right? If you give force in these 2 directions, so overall component is going in this direction. So obviously this will be something like this. Until when? Until the 100 radian per second, because before that nothing is changing. Before that nothing is changing. So we'll just write this in short here. I can reduce the size of this one furthermore, like until 100 it is changing here. Now now what is happening? Now basically you can reduce the slope further. You can reduce the slope further because after this uh, the slope here is reducing. Okay, it is also reducing, and this is cancelling this one out, but this one is extra term, extra slope. So obviously my slope will reduce here. So one thing I had to do was like this will actually at, just let me check at omega equals to 1 what is my magnitude, so whether it will cross the 0 dB line or not. Okay, I haven't even drawn the 0 dB line. Okay, it is starting from this minus 20 dB only, so it doesn't matter. So here it will be something like this after this, right? Okay, so this will be my Bode plot. Here in this region, my slope will be plus 20 dB per decade. In this region, let me use some other color. What color shall I use? This one is good. In this region, what is my slope? 0 dB per decade. So this is not plus, this is minus. Here I have slope of 0 dB per decade. Here I have slope of minus 20 dB per decade. So like I hope you are understanding the different regions here, right? That is very important to understand the different regions. Where is my slope minus 20 dB per decade? Where is my 0? Where is my, so this is the Bode plot actually. This is a Bode. I don't know, this is a mess right now, but this is so simple, isn't it? Just straight lines and just a summation of all this. Obviously when we will draw Bode plots, we won't have to draw all this mess. This is just for making you understand that what is actually happening in the graph, what is actually happening. All these things are getting added. Okay, when we'll go to the step procedure, we don't have to do all this. Just in one shot we will draw this directly. Just will be, if you are uncomfortable, you can draw this table and start off, or if you are very comfortable, you can directly start off with the graph itself. Very easy, not that difficult. Okay, so this is the Bode gain plot. Now let's go for the Bode phase plot. Now this is a bit tricky. Okay, when the number of like corner frequencies increases, then plotting the Bode phase plot becomes very tricky. If there is intersection between these two, what do we mean by intersection? Let's see. Here I am talking about omega between, like the slope, this is present between omega greater than 10 and less than 1000. Here I am talking about the slope between omega greater than 0.01 and 1. Here I am talking that my slope is within this region 0.1 to 10. So this region and these region are getting overlap. Also this region, this 10 region, okay, these are not getting overlap. That is good. So this region is totally separate. This region is totally separate. That is good. Now this region and these region are getting overlap. So whenever there is overlapping, then the Bode phase plot is bit difficult. Because we have to add the slopes in between. So what we do is, like whenever there is overlapping, then we go from the minimum to this. So this is the minimum. So we go from the minimum to the next minimum. So this is 0.1. Then we start from the next minimum to the next minimum. So this is 1, and then again we start from 1 to 10, and we stop there. Okay, so this is how we will do. So what is the minimum here? 0.001. So like when you are plotting the Bode phase plot, I will recommend you to plot like this, what I am doing here. Okay, so here I have 0.01, that is a minimum. Okay, then if I go from minimum this 0.01 to what is the next minimum, like these two are overlapping, right? These 0 and polar overlapping, to 0.1, 0.01 to 0.1, 0.01, 0.01 to 0.1. Let me just write the thresholds and then like ranges. Then we will solve for the slopes. Okay, so we'll write this overall slopes. This is not slope, actually this is a slope. and this is in radian per second. Okay, so point, now we start from point 1 to not 10, because we have another minimum number, that is 1. So 0.1 to 1. Okay, this is a bit hectic, so just bear with me. And the more the overlapping is, the more difficult it gets to plot the phase plot. 1 radian per second, and then we have 1 to 10. So this is 1 and this is 10. So 1 to 10. After this, it is easy, because after this, that's overlapping is gone. Overlapping is gone. Now we have only this range, right? 10 to 1000. So this is pretty much easy. 10 to 1000. Okay. Now what is happening here is that I have overlap here. What do you mean by overlap? So 0.001 means what? 0.001 means this, I have a pole which is contributing, like just greater than 0.001, which is contributing a slope of minus 45 degree per decade. That is fine. That is fine. Now what is happening at 0.1? Like this is contributing a slope of plus 45 degree per decade just after 0.1. Just after 0.1. So before the 0.1, it is contributing what? 0. Before 0.1, it is contributing 0 degree per decade. So what is present? Only one pole is present between this 0.001 to 0.1, because just after 0.001, this is contributing me minus 45 degree per decade slope, and just before 0.1, this is contributing 0 degree per decade slope. Okay. So also here also you can understand this is also contributing 0 before 10. So like this also satisfies the 0.1 condition also. So like here, why like we are adding this one up? Because you remember these are the summation of the tan inverse formula, tan inverse omega p, tan inverse omega z, whatever it was, right? Summation of those. So I'm just adding those up, whichever angle each one of them is contributing, with the approximate analysis. I hope you are recalling everything. So here I have only, in this region I have only one pole present. So I can write here, in this region only one pole. Okay, like the pi pole, it's not actually the pole present, it's just the contribution of the pole, one contribution, angle contribution. It's not the actual pole. So this one becomes, like, as we have only one pole, so this one becomes minus 45 degree. So, and this is due to one pole itself. Okay, so in this region we have only one pole, and this one becomes minus 45 degree. Now what about this 0.1 to 1? What about this 0.1 to 1? So like between 0.1 to 1, what do I have? So here, if I observe this carefully, so this 0.1 is lying in this range, so this will contribute minus 45 degree per decade. That is fine. Now just after 0.1, this is also lying in this range, right? Just after 0.1, between 0.1 to 1, so this will also contribute plus 45 degree per decade slope. So hence, what is my overall slope? I will just simply add them up. So simply adding them up gives me 0, right? Because I have a pole plus 0 in this region, and this is not even lying in this region. This pole is not even lying in this region, because this is between 10 to 1000, so this is not contributing to anything. So we haven't even reached 10 yet, so we don't care about that last pole. Now 1 to 10. 1 to 10, what is happening? 1 to 10, so the effect of this one is finished, because it was until 1 it was contributing minus 45 degree per decade. Just after 1, this is contributing 0 degree per decade. The effect of this one is finished, but the effect of this one is still present. Okay, because this is 1 to 10, so this lies in this range, so we will still get 40 plus 45 degree per decade slope, but this one we won't get any slope. Why? Because this is after 10, so we haven't even reached 10 yet. This is between 1 to 10, so obviously I will get only one slope of plus 45 degree per decade. Okay, I won't write degree because degree is already written there, and this is only 0. Okay, so I will write here just and here we are getting only one angle contribution, 0. Here we are getting only one angle contribution. Again this is Z2 pole. The effect of 0 goes away. The effect of 0 will be gone. So this is pole. Okay, so like you can see, like this effect of 0 has gone. Effect of 0 is placed before 10, so after 10 obviously only this one is existing, so we'll get minus 45 degree per decade slope. This is simple. Okay, suddenly the slope changes from plus 45 to minus 45. One more thing I forgot to tell you. I told you one formula, right? I think I told you some formula here. This formula I told you that the slope of the magnitude plot to 10 to minus 20 dB into n minus m per decade slope. So here, what is n minus m? Number of poles. What is number of poles? So here n is 2, m is 1. So slope as omega tends to infinity, basically high frequency region, minus 20 into 2 minus 1 equals to minus 20. Now is this the case here? Is this the case here? Yes. What is slope? Slope is minus 20 dB per decade. So like this also you can cross verify whether you did the Bode magnitude plot right or not. Also the phase plot also will cross verify. Okay, like this you can cross verify. Okay, you are checking that yes, it is giving me minus 20 dB per decade slope. Okay, minus 20 dB per decade slope. Okay, very important. So yeah, this is one point I wanted to tell you. Now this is another point. Let's draw the Bode phase plot. Now we have got the slopes of each point. Also, like at omega equals to 0, what slope we are getting? We are getting 0 slope. So at omega equals to 0, we are getting like around 0 slope. Then what is happening? Suddenly at 0.001, we have a slope of minus 45 degree per decade. So this is minus 45 degree per decade. Then like this is the individual plots. Okay, this is the individual plots. Let me explain the individual plots. So this is the constant magnitude plot. So this will give me 0 phase. Now this is the phase plot due to the pole. Okay, at omega equals to 0.1. So 10 times before this, 10 times after this, the effect of slope will be minus 45 degree per decade. After this, the slope will be 0. Before this, the slope will be 0. Constant numbers. So this is the pole. What about this? So this one, if I see that this is the pole at omega equals to 100. So 10 times before this, the slope is almost 0. 10 times after this, the slope is 0. And in between this range, the slope is minus 45 degree per decade. Okay. So these are the two poles. And let's talk about the zeros. So here, this is 0 who has corner frequency of 1 radian per second. So it is here. Okay. Not exactly like, okay. Yeah, fine. This is okay. Yeah, here. This is here, right? Corner frequency of 1. So 10 times before this and 10 times after this, the slope is like this range is 45 plus 45 degree per decade. And after 10, this becomes 0. Before 10, this becomes 0. Okay. So this is the these are the individual plots of the blocks. Now let's add them up. You can either add them up, but sometimes adding them up is difficult. But let's do it with both methods. Let me first add them up, then I will do it in that method, in the table of slope method. So overall we'll follow this method only. Okay, but just for explaining you what is actually happening in the Bode phase plot, we're doing it like this. Okay, but this is time consuming, right? Plotting each of them, then adding them, this is time consuming. Just put a table and take the slopes and just plot it there. Okay, that you can do. So yeah, let's first do this with simple algebraic sums. So first, before this 0.001, everything is 0. So I start with 0. Let me start with 0. So now after 0.001, what is happening? this is providing me a slope of minus 45 degree per decade. Everything else is 0. So I will follow this one. I will follow this one until here. Until here, because again I encounter a 0 which is also providing me plus 45 degree plus slope. So obviously I will become constant until here. Okay, because here some slope change is there, but before that, where is the slope change? Slope change here is also there. So before this one slope change, here is also slope change. So it becomes from minus 45 to 0. So 0 plus 45, and this is 0. So it becomes overall plus 45 degree per decade. So I will go until here, and I will add these three up at this point. So I will getting plus 45 degree per decade. So I will follow this one. Okay, and I will go until here. This is 10, yeah. Now here what is happening? This is providing 0, this is providing minus 45, and this is still providing plus 45. Is it? No, this is also, this is providing 0. Okay, that's why, like, this is not exact, just please don't go by this. So overall what is happening at 10, we remember, right? This 0 provides 0 phase. This pole obviously has gone to 0, this won't change, but suddenly this pole comes into effect. So I will get overall minus 45 degree per decade, and it will keep on going like this until here. Okay, until here it will keep on going. Now please don't go by the exact values. What are the exact values? Because I haven't calculated it. Okay, just the shape of the Bode phase plot I'm explaining you. How is the shape? By shape I mean the what are the slopes at each particular region. That is more important. The angles, please don't go by the angles. The angles may be different. Okay, it may be different, but the shape will be same. Shape will remain same. The exact values, if you just check, it may be different if you exactly plot this Bode phase plot. Okay, so I'm just interested in the phase slopes of the phase plot. So let me break it down. So in this region my slope is 0 degree per decade. Okay, in this region my slope is minus 45 degree per decade. In this region my slope is 0 degree per decade. In this region my slope is plus 45 degree per decade. In this region my slope is minus 45 degree per decade, and here it becomes 0 degree per decade. So yeah, so this is the case. Now let's cross verify it. Let's cross verify here what I was talking about. Like before, obviously 0.001 my slope is 0, nothing is changing. So before 0.001 my slope is 0 degree per decade. Good. Now between this 0.01 to 0.1 my slope is what? Minus 45 degree per decade, even though it's not correctly in axis symmetry, but just understand, between this 0.001 to 0.1 this is minus 45. Yeah, this is minus 45. Good. Now from 0.1 to 1 slope is 0. Slope is 0. 0.1 to 1 slope is 0. Now from 1 to 10 my slope is 10. Okay, let me just, okay, if you, now this is perfectly, like, even if it's perfectly not aligned, you can understand, right? Between 1 to 10 my slope is 45. Okay, and here also it mentions 45. Now after 10 to 1000, between 10 to 1000 my slope is minus 45. So between 10 to 1000, okay, my slope is 10 to 1000, my slope is minus 45, and obviously after this it becomes 0. Okay, so obviously we will do this using this table. We will not obviously draw all this, that will take more time consuming. So we'll do this using this table. Okay, so I'm just doing the cross back calculation. So here you can understand, yes, this plot is correct. Now let's do it like one thing you can cross verify is for the phase plot where it will end. I mentioned one key point where it will end. Yeah, your phase plot would tend to minus 19 to n minus m. So angle, like if you want to cross verify, right, if the Bode phase plot is given and you want to cross verify in the exam whether this is the correct phase plot for that particular transformation or not, what you can do is simply angle of g of j omega as omega tends to infinity equals to minus 20 n minus not minus 20, minus 90 n minus n, basically number of poles minus number of zeros, which is minus 90. so it will end at minus 90. So like according to this, like it should end here. Okay, it should end here, not here. So what I will do is just I will change a few things. I will just reduce, I will delete all this. Okay, like this is not to scale, not to scale, please. Like this is just a, like what I'm explaining the shape of this one. Like the values may change. Okay, I haven't calculated anything. So yeah, this is not to scale. So here, like what we can understand is that from point 1 to 1 it is moving 10 times. So the slope is minus 45 degree per decade, so it should reach minus 45 degree, right? So for each decade it is moving down by 45 degrees. So obviously here the value should be, here the value should be minus 45. So let's do that also. So this value will be, let's plot it to scale now. So this value is minus 45 degree per decade. Now this is constant, so this is remaining at minus 45 degree. Then suddenly from 1 to 10 it is again moving 1 decade, and the slope is plus 45 degree per decade. So again it will reach to 0. So this is symmetric. Now what is happening after this? My slope is minus 45 degree per decade, and how many decades am I moving? I am moving total 1 decade and then another decade. 2 decades I am moving. So 1 decade if I move down by 45 degrees, so I reach here. Then again another decade I'll move by another 45 degrees. So overall I will stay at 90, minus 90, and then obviously it will go to constant. So yeah, this is basically what Bode phase plot would look like, and this is how you can cross verify also. Like you can do this like this, right? What does minus 45 degree per decade mean? It means for every decade I am moving in the y-axis I am moving by 45 degree. As if this is negative, I am moving down. If this was positive, I will move up. This is positive, I am moving up. This is negative, I am moving down. So between 0 to 0.01, not 0 exactly because we can't plot 0. Before 0.01, I have a 0 degree per decade slope, and my angle is also 0. Because why? This constant has 0.1. This is providing me 0 slope. Now after this, what is happening? For each decade I am moving, I have got a slope of minus 45 degree per decade. So I have moved from 0.01 to 0.1. So I have moved 1 decade, and the slope is minus 45 degree per decade. So each decade I'll move down by 45 degrees. So that's why I move down by 45 degrees. So this value is minus 45 degrees. Now after that, slope remains constant, so obviously value won't change. After this, slope increases to plus 45 degree per decade. So what will happen? I will move up by 45 degrees, as I have only moved for 1 decade. No, from here, from 1 to 10, 1 decade I have moved. So yeah, so like this. So yeah, I hope you get the point. Okay, so these are few key points about Bode plot. But first, like I hope you understand the concept behind the Bode plot and how to draw the Bode plot, right? So yeah, like this is very interesting thing. So if you haven't understood, please do watch the video and repeat, because this is the most important part. So what we'll do, we'll mainly just use the table and just plot it. We won't obviously draw all this individual blocks, because that will be very time consuming. And here also we'll just draw the table of slopes and do this as I backtrack. This is giving me the right results. Okay, that's why we will use this. So what are the key points about the Bode plots? In control systems, Bode plots are used to describe the frequency response of open transfer function, but in general it can describe any frequency response. Closed transfer function, it can describe anything. So yeah, but in general in control systems we use Bode plot to describe the frequency response of OLTF. Bode plot describes the relative stability of closed loop system by using the frequency response of open loop system. Like it can also describe the omega GC, omega PC, gain margin, phase margin. How can I describe? Here from the magnitude plot, what information can you get? Wherever it crosses the 0 dB axis, that is my gain crossover frequency. At whatever frequency, that is my gain crossover frequency. And if you know the gain crossover frequency, and here whatever the gain crossover frequency, the phase is at the gain crossover frequency, if you just add 180 with that, you will get your phase margin. Good. Okay. And how to find the omega PC? Here you check wherever my phase is reaching minus 180 degrees, you find the frequency for that, and that frequency you put here. Okay, and you find the omega PC. Now you find the omega PC and find the gain of this one. Okay, and you just negate the sign of this one, because reciprocal in absolute scale is change of sign in dBs. Why? Because like what is gain margin? Gain margin was, just doing this in rough, 1 by g of g omega, magnitude of g omega equals to omega PC. Okay, inverse of this one. So if I want to take log of this, log of this 1 by x. What does this become? This becomes minus log of x. So simply, whatever the log of x is, whatever the magnitude here is, like this is mod of g omega, right? Whatever the magnitude here is, simply negate the sign. So here, if we can find the magnitude here and simply just negate the sign, we'll get our what? We'll get our gain margin. Okay. So yeah, this is about this point. Now Bode plot is a combination of two individual plots. Individual plots, approximate magnitude plot and approximate phase plot. This we already know. This is just a few key points just to keep this all this in your head. Whenever revising, you can read this and yeah, you can recall, yes, this concept has been taught. Yes, I remember this, all these things. And effect of addition of poles and zeros can be easily analyzed by using Bode plots. Here, just simply if you add another pole, what will happen? Simply this will be algebraic sum, right? The slope will be algebraic sum. So addition of poles and zeros can be easily analyzed here. That's why we use this Bode plots for analysis. Okay, very simple to analyze. Now Bode plots is analyzed only for minimum phase system. Now as this lecture has gone, we won't be able to start our minimum phase system. We'll start our minimum phase system in the next lecture. So we'll learn about minimum phase system and non-minimum phase system in the next lecture. So yeah, thank you for watching this video, and I will see you in the next lecture with minimum phase system.